So if you recall from your original studies in geometry, you know about the area of a circle, right? If you have some sort of radius, you can define that area as pi r squared. Simple enough, right? And if you keep going, you remember when you did volumes, that you had the volume of a cylinder. And that volume, what you actually had is you had this idea of a prism. And any prism has an area of a base, and then you sort of think of it as kind of like pulling it into the third dimension. So you can create this volume. But a cylinder is kind of special in that a cylinder has a circular base, and then it's pulled up, and there are other special properties as well, but generally speaking, a cylinder is just a type of prism with additional properties where the area is the circle, and then it was pulled up some height. So a lot of times we think of what's called as right circular cylinder. I apologize. There's the idea of a right circular cylinder, and that's this. It has that circle here, and then at a right angle it comes up. And we could think of that as being laying on its side as well. And that's going to be useful for what we're doing today, is that you have some sort of radius here, and then you have that height. When it's on its side, the height is kind of an odd thing to think about when it's laying on its side. The height is here, but you can think of it like there. So why are we doing this? Well, we're doing this because we're going to use some interesting techniques in calculus to extend or generalize the idea of a cylinder as you might think of it. So take a look at this kind of vase. It's a pretty terrible vase, at least from that the way I constructed it, but it smoothly goes like this, right? It doesn't just go straight up and down, it kind of moves. And so you might ask yourself, well, how in the world would I get the volume of that? If I had a vase and I set it down on the counter, how much water would I need to pour into it? Now, obviously you could figure that out by just pouring water into it until you were done. But that's kind of that's how reverse engineering works. We're looking at forward engineering here. And in forward engineering, what you do is you describe the object and use mathematical constructs to solve for the answer without having to empirically test. So anyway, I say all that because we can actually use the same sort of idea that we have here. So what we really do is we could think of this as being cut into several pieces that are about the same size. So each of these pieces is what would be called discs. That's why we're dealing with what's called the disc method. And those little discs, if you added them up together, would approximate this shape, right? They wouldn't exactly stack together because you would have to slice them. But if we started slicing them more and more thinly, that those thin strips would start to resemble what we're doing here. And that's that's a really interesting idea, because what we're doing is we're using the techniques that we learned in calculus about developing those strips, but we're not doing strips that are rectangles. We'd be doing strips that are discs, and we'd be summing up those discs together to approximate, and then eventually, through the limiting process, determine the volume of that vase. Now, there's an alternative way to think about this that I think is a little more intuitive than doing the standard calculus way. So what you're really saying at any given moment is you're saying, okay, well, if I take a slice, if I slice this at any moment, I have a circle, right? If I slice this, there's a circle here. If I slice it, there's a circle there. And so on and so on. I have all these circles. So what if I define some sort of function, some sort of volume function that is just simply saying, all right, at any given moment, I'm going to have some sort of axis of revolution, and then I'm going to have some sort of height to this, or not height, sorry, some sort of radius of that circle, right? Again, if I do a slice here, that cross section has a radius because these are the same center, so those are the same idea, right? So it's that. Now, if we go over here, we kind of have that idea. We say, all right, I'm going to start at some value, some starting value A, and I'm going to end at some starting or ending value B. And at any given moment, I have a function value that serves as my radius. So what I can do is I can say, okay, at any given cross section, at any slice, I have pi, instead of r squared, it's f of x squared, right? So pi r squared. So at any given point, I have a circle. And if I sum up all of those areas across the entire length, if I just sum all of them up, I get some sort of like pi r squared h, right? It's not r squared because the radius is changing, but you get the same idea. You get that same cylindrical volume. It'd be the same idea as if you took this cylinder and you just took circle, 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 and stacked them. You'd have pi r squared h. So let's use that idea with a constant. If I said, okay, all right, let's take a step back. What if I just said, okay, this is a constant. It's a constant flat radius, which means we're dealing with this cylinder here. If we do that, we let f of x be a constant. We have the volume is equal to pi, again, that's r squared dx. Now, in this case, neither of those have x's in it, so we can actually pull that out front. And so we just have the integral from a to b dx here with pi r squared in front. Well, the integral from a to b dx, well, it's just going to be b minus a, right? That's just the constant function 1. So this is pi r squared times some length, which is your height, right? That is the height of your cylinder. So the idea here is that this not only matches the traditional geometric representation when f is a constant function, it allows us to extend that even further to talk about general functions, to say, okay, how do I describe something that looks like this? How do I meaningfully do that? And we're going to be doing some examples to really get more into this, but I do want to say one little thing before we go, which is the way I always envision this, and this is kind of a weird way, is what we're trying to do is we're trying to take this function, instead of the area, if you think about that area under the curve, right? If I went up here, the standard integral we have is this area under the curve. And we have this sort of axle that we've jammed right through it. If we took that area around that axle and we slapped it and it went and spun around, really, really quickly, it would look like that 3D image, right? Because it would be going, and that's, so if you've ever watched like clay pot making, or I think it's called throwing or whatever, but if you look at that, the idea is you're spinning it and it's being shaped as it goes around. And that's the idea. What we're doing is we're taking this and just slapping it and just, and as it goes, it generates this shape, and we want to know what the volume of that generated shape is. So we're going to do some more examples, and hopefully this will get you a little more familiar with what we're doing.